Good morning, friends. I feel immense pleasure to be here for my course, Engineering Thermodynamics. I am in the process of air standard cycles. As of now, I have covered the Otto cycle and the diesel cycle. I have described about the processes in Otto cycle and processes in diesel cycle and how they differ from each other. I have also done the derivation for the efficiency of Otto cycle, the work done by the Otto cycle, heat rejection and the heat addition and heat rejection of the Otto cycle. We have also find out the pressure and the temperature of each point on the Otto cycle. Same way we have already done by the this diesel cycle. In diesel cycle, the ignition is taking place at the constant pressure process. However, in Otto cycle, the ignition or the heat addition is taking place at the constant volume process. So this is only the basic difference. For the given compression ratio, the efficiency of the Otto cycle is better than the efficiency of the diesel cycle. That we have seen that what is the effect of cutoff ratio, that is rho. And as you increase the cutoff ratio, the efficiency of the diesel cycle is decreases. So how much is optimum is required? So in this process, we have seen that the next is the dual cycle. The dual cycle is taken the combination of Otto cycle and the diesel cycle. So in this, I will be discussing today about the dual cycle, the mathematical analysis of the dual cycle. And the previous classes, we have seen the introduction to dual cycle for our mixed cycle, dual cycle operations and dual cycle processes. So this, before that, if you see that, if this is the PV diagram of Otto cycle and another is PV diagram for a diesel cycle. I am writing here diesel cycle. So if you see here, 1 to 2 is a isentropic compression, 2 to 3 is isochoric. This is the isochoric heat addition, that is Q in. From here it goes like this, and from here to here it is isochoric heat rejection, or this we can write it as a Q out. Here this is the expansion process. And here heat is added, and if you see, it is used, Otto cycles are used for spark ignition engine, spark ignition engines. And if you see the diesel cycle, so compression is almost same, 1 to 2 is same, but heat addition is at Q in at constant pressure, and from here it is going like this. This is the expansion, adiabatic, or it is also called isentropic. So if it is a reversible adiabatic, it is called the isentropic. So here this is the 1, 2, 3, and this is 4, and this is the 1. So here also it is 4 and 1. So here the basic difference between Otto cycle and the diesel cycle is heat addition. In diesel cycle, heat addition at constant pressure process, and in Otto cycle the heat addition is at constant volume or isochoric process. So this is the basic difference between it. If you see here the 4-1 of Otto cycle and 4-1 of diesel cycle, both are at the constant volume or the isochoric heat rejection. So here also it is the heat rejection, Q out. Here is the Q in. This process 4-1 is same, 1 to 2 is same, 3 to 4 is same, only 2 to 3 here and 2 to 3 here is different. So here what happens that if we take the Otto cycle, in Otto cycle, if you see this is the, I'm just drawing here, if you see, this is the piston, it is a cylinder and this is the piston here. This is the piston. So when it is reaching to TDC and here is the BDC. So at the TDC when it is reaching, then only at that instant of time, within a very fraction of time, in nanosecond, it has to, full fuel has to burn. So that is practically not possible. So the diesel cycle was developed, but in diesel, what happened? From here to here, there are reduction in the efficiency due to this burning process. Here, the work is not done. But if you see, the work is done from here to here. But here it starts from here. This much percent, it is called cutoff ratio. And this cutoff ratio is the problem. And here, we will not get the proper efficiency. So both processes are not in the real, it is not possible. Then that is why the dual cycle was developed. So in this dual cycle, what happened? After this much, it is made like this. So the dual process, we have the two. Here is Q addition and here is the Q addition. Means Q1 2, Q in 1 plus Q in 2. This is the heat addition in the 2 process. So that we have to see, and now I am going to discuss about the dual cycle. So dual cycle or limited pressure cycle is a thermodynamic cycle that combines the Otto cycle and the diesel cycle. In the dual cycle, combustion occurs partly at a constant volume. So I will write here. So from this is the process 1, and from here if you see, this is the isentropic compression, and so this is the isentropic compression, and this much is your constant volume. So 1 to 2, 2 to 3, and from here this much, this is the 3 to 4. This is the these are the Q in. So dual cycle or limited pressure cycle is a thermodynamic cycle that combines the Otto cycle and the diesel cycle. So 2 to 3 is the Otto cycle and 3 to 4 is a diesel cycle. So it is a combination of both. That is why name was given the dual cycle. In the dual cycle, combustion occurs partly at the constant volume and partly at constant pressure. We need to find out the mathematical analysis of the cycle with thermodynamic properties at each point on the process where dual cycle is used. So here we have to use the dual cycle. In a diesel engine, the dual combustion cycle is used. The dual combustion cycle is an ideal air standard closed cycle with 5 operations. In the diesel cycle and the Otto cycle, there was only 4 operations, but in the dual cycle, 1 more operation is increased comparing to the Otto cycle and the diesel cycle. The first of which is a heat addition at constant volume. So at a constant volume, heat addition is taking place, followed by heat addition at a constant pressure. So here this you can see, this is the constant volume 2 to 3 and this is the 3 to 4. These both are heat addition at constant V and P. And finally, rejection at a constant volume. So here if you see, from here this is the expansion and here this is the 4, 5 and 5 to 1. This is the rejection. So we can see that this is happening like this. So we will be now deriving the equation for dual cycle, and we can see that mathematically we need to find efficiency and state points on this cycle as we have done for Otto cycle and the diesel cycles. So here I have shown the PV and the TS diagram. So first I will discuss about the PV diagram. So in PV diagram 1 and 2 is a isentropic compression. So this is the S is equal to constant. From 2 to 3 it is a isochoric heat addition. And this 3 to 4, this one is a isobaric heat addition. Okay, isobaric heat addition. 4 to 5 is a isentropic expansion, where S is equal to constant. Okay, so delta S is equal to 0 or S is equal to constant, and 5 to 1 is a heat rejection at constant volume. So this is the PV diagram. If you see the TS diagram, so this 1 and 2 is an isentropic process, isentropic compression. So the temperature will increase. So starting from the 1, this is the point 1 here, it is P1 and the T1. So this is the T1 here. In this case, the some entropy is here. This is the S1. So from 1 to 2, it is isentropic process. There will not be any change in entropy. Entropy will remain the constant, and the pressure and the temperature will increase. Pressure we can see from here, that from 1 to P2 here, but temperature we cannot see in the PV diagram. So we have to use the TS diagram. So this 1 to 2 is your isentropic compression. So in this pressure is increased. Now 2 to 3. 2 to 3 is isochoric or constant volume heat addition. In this, the 2 to 3 process is having more slope than the 3 to 4, because 3 to 4 is a constant pressure process and 2 to 3 is a constant volume process. So this 2 to 3 is a constant volume process. Here heat Q in 1. This is a Q in 1. And if you see the next one, 3 to 4, here 3 to 4, it is a Q in 2. So means here two ways of heat addition is added, Q in 1 and Q in 2. From 4 to 5, it is a adiabatic, that is S is equal to constant. Here 4 to 5, it is expansion is taking place. So here temperature is falling down, sharp decrease in the temperature is experienced, and from 5 to 1 is a isochoric. This is isochoric heat rejection. Okay, so this is the Q out. So here Q in is equal to Q in 1 plus Q in 2, and heat rejection is Q out. Okay, so here if you see, the area of this thing will give your heat rejected or the net heat, and by the first law of thermodynamics, the del Q is equal to del W. So if you can find out the heat added or heat rejected or the net heat supplied, you can get the net work done. And from here also, the area of this PV diagram is giving the work done, W is equal to PdV. So by this we can find out, by the both method we can find out the work done. Here some new terms are coming. First one is the compression ratio. I am writing here RC. This RC is equal to V1 by V2. Fuel cutoff ratio, that is rho, is equal to V4 by V3. So here just you can see the compression ratio V1 by V2. So here is V1 here. This is the V1 and here is the V2. So V1 by V2. So this V1 is a full volume and the V2 is a residual volume. That is the left in the cylinder. So compression ratio is the ratio of the compression. So this is from here to here. V1 by V2 or P2 by P1. That also you can write it. Fuel cutoff ratio. Here if you see, fuel we give from 3 to 4. So here we will write that V4 by V3. So V4 by V3 and V3 is equal to V1. This is the V4 and this is V1 and V1 is equal to V3. Now another is expansion ratio RE. So expansion ratio is the ratio of V5 and V1 is equal to V5. So V5 by V4 is your expansion ratio. Also we can take the pressure ratio, that is 2 to 3. So here P3 by P2 is a pressure ratio when V is constant. Okay, so in this isochoric process we use the RP is equal to P3 by P2. So these are the few ratios which will be used for derivation of our problem of dual cycle analysis. So we have to start with how to find out the efficiency. So efficiency can be defined as eta is equal to 1 minus heat out by heat in, or heat rejected by heat supplied. So 1 minus Q out by Q in. So I have told you that Q in is in a two part, that is one is at the constant volume, another is the constant pressure. So Q out will be CV T5 minus T1. So just I will draw here. So initially like this, then like this, like this, like this. One, two, 3, 4, 5. This is the T and this is the S. So here you can see the process. So if you see the 1 to 2, it is a compression. Here it is a Q in when V is a constant, and here is Q in 2. This is Q in 1, and when P is a constant. Okay, so here and Q out is 5 to 1. So this is the T5 and this is the T1. T5 by T1. So what is the heat rejected? It is a CV because it is a constant volume process. So here Q out is equal to CV, a specific heat at constant volume, T5 minus T1, and Q in is equal to Q in 1, that is the constant volume heat addition plus constant pressure heat addition. So you will get here CV T3 minus T2. This is the T3 here and this is the T2. So T3 minus T2 plus, because it is a constant pressure process, so plus CP T4 minus T3. So you got the Q in. So we have seen here that 1 minus Q out by Q in. So 1 minus CV T5 minus T1 as given here divided by CV T3 minus T2 plus CP T4 minus T3. So 1 minus, we will divide. So CV, it is cancelled. Here it will be CP by CV. So T5 minus T1 divided by T3 minus T2 plus CP by CV, T4 minus T3. So this CP minus CP by CV is equal to gamma. So this gamma here, this is the gamma here. So 1 minus T5 minus T1 divided by T3 minus T2 plus gamma T4 minus T3. So this we have got. Now here we can see that we have the 5 temperature for each point starting from 1, 2, 3, 4 and 5. We have the temperature. So we have to find out all the temperature with respect to T1. We will relate all the, so if you know the T1, you can find out all the temperatures, and this will be used for the future numericals and other things. So in the above equation, we have 5 temperatures, that is T1 to T5 for each process. We need to find the relationship for each with respect to T1. So we need to represent each temperature with respect to the T1. So now taking the process, just I am drawing here one small PV diagram like this. So Not very much correct. No problem. 5. Okay, so this is a PV diagram. Okay, so here we can see that process 1 to 2, it is a adiabatic compression. So here Tv to the power gamma minus 1 is equal to constant, or we can write that T2 by T1 is equal to V1 by V2 gamma minus 1. We are writing always V1 by V2 because V1 by V2 is a, here if this is a V1 and this is the V2, so V1 by V2 is a compression ratio RC. So RC gamma minus 1 because RC is equal to V1 by V2. So here we got that T2 is equal to T1 RC to the power gamma minus 1, and this is the equation number 1. Now we have to find out at constant volume 2 to 3. It is called isochoric process, taking process 2 and 3. So we can write here that P3 by P2 is equal to T3 by T2. Okay, so this P3 by P2, it is called the compression ratio, it is called the pressure ratio RP. P3 by P2 is equal to RP, it is called the pressure ratio. So from T3, it is T2 RP. But T2 from equation 1A, T2 is equal to T1 RC to the power gamma minus 1. So here T3 is equal to T1. For this T2, we have to write from here. So this T1 RC to the power gamma minus 1 into RP. So we got the second relation with T3 and we got the T2. So T2, T3 we have got. Now we have to find out T4 and the T5. So further I am going to explain how to find out all the state points. Each 1, 2, 3, 4, 5, P1, T1, P2, T2, P3, T3, P4, T4. All points if you know, we can do all the calculation. In your exam also, this they will ask that at state 1 the maximum pressure or the maximum temperature. So maximum pressure in this case will be at P3 and the P4. And temperature, we can also see that at P4 you have the highest temperature. So like these questions, it may arise. Now if you take the process 3 and 4, so this 3 and 4, if you see here, it is like this. This is the 2, this is the 3, so 3 and 4. So it is a constant pressure process from here to here. So in this pressure is constant. So using the Charles law, the volume is directly proportional to the temperature when pressure is constant. So V4 by V3 is equal to T4 by T3, or T4 by T3 is equal to rho. T4 by T3 is equal to V4 by V3, and V4 by 3 is equal to rho. That is known as the fuel cutoff ratio. So T4 is equal to T3 into rho. And where T3 is equal to, we can take from the previous lecture that T3 is equal to T1 RC to the power gamma minus 1 into RP and into rho. So we got another equation. In this equation, we got the temperature T4. So now we got this T4 also we got, T3 we got, T2 we got. Next, we have to find out T5. This is T5. So in the next, we will see, and this is the expansion ratio. 4 and 5 is a expansion process, reversible adiabatic expansion or isentropic expansion. So we have to use that relationship. So here T4 by T5 is equal to V5 by V4 gamma minus 1. So what is this? I will just write here again. It will be very much easy. So PV. So 1 to 2, 2 to 3, 3 to 4 and 4 to 5 like this. Okay. So 1, 2, 3, 4 and 5. So here T4 by T5 is equal to V5 by V4 gamma minus 1, and V5 by V4 is equal to, it is called expansion ratio RE. E stands for expansion ratio RE gamma minus 1, or we can write T5 is equal to T4 divided by RE gamma minus 1. So here we can put this value here. So this T5 is equal to T4 RE gamma minus 1. So T5 is equal to T4 divided by RE to the power gamma minus 1. So T4 is equal to T1 RC to the power gamma minus 1 into RP into rho, that we have seen in our previous discussion. Here if you see that rho into RE is equal to RC. So this rho is equal to RC by RE. So here we can write here T1, this RC by RE gamma minus 1. So RC by RE, you can write the rho to the power gamma minus 1 into rho. So R T1 rho to the power gamma minus into so this rho is cancelled. So here you will get T1 rho to the power gamma into RP. So this is equal to your T5. So T5 is equal to T4 T1. This is the T1 here. T1 into rho to the power gamma into RP. So now we got T2, T3, T4 and T5 with respect to T1. All are having. So now we will see here the efficiency. So this N is equal to 1 minus T5 minus T1 by T3 minus T2 gamma T4 minus T3. Putting all this value T1 rho to the power gamma RP here. So you will get efficiency is equal to 1 minus rho to the power gamma RP minus 1 divided by RC gamma minus 1, and at the final you will get efficiency of dual cycle 1 minus rho to the power gamma RP minus 1 divided by RC to the power gamma minus 1 RP to the power RP minus 1 gamma RP rho minus 1. So this is the efficiency equation for the dual cycle. Okay, hope you have understood very well. So efficiency of the Otto cycle is 1 minus 1 by RC to the power gamma minus 1. Diesel cycle is 1 minus RC gamma minus 1 rho to the power gamma minus 1 divided by gamma rho minus 1. And here if you see, only we have to add one more term here, gamma rho to the power gamma minus 1 into RP. Here we are multiplying RP and here also we are multiplying RP and minus 1. So this is the, and these are the next Brayton cycle, introduction and mathematical analysis. These are the references which I am going to take. Thank you very much for joining the class.
Like, share and subscribe. Hit the bell icon for more updates.